Okay, good morning everyone. Welcome to the Australian Centre for LNG Futures Public Lectures. I'm Jill Steiderhaus, Centre Manager, and it's my pleasure to introduce you to the first of a series of public lectures that will be presented over the coming months, in which the Centre's key achievements and industrial significance will be presented. Today, I'd like to welcome Professor Eric May, Director of the Centre and Chevron Chair in Gas Processing, who will be speaking to us on two industry-led projects. The first on boil-off gas prediction to optimise LNG storage and shipping, and the second project on technologies for assessing blockage risk in cryogenic heat exchangers. As I mentioned, Eric will be taking questions at the end of the presentation. Please use the raise hand function if you'd like to ask a question after the presentation. Eric, over to you for this morning's lecture.
Thank you, Jill, and great to have everybody on board. Let me just share my screen. Can everyone see the slide deck, the title slide? I'll take your silence as a yes. Right, so as Jill mentioned, I'm just going to deal with this, okay? Thank you for your time this morning and attending this virtual public lecture. It's the first time for me doing one with this number of people. Hopefully it'll work well and we'll be able to give either in person or virtually a few of these over the next 12 months as we describe the outcomes produced by the Australian Centre for LNG Futures. So about just over 5 years ago now, the first ARC Industrial Transformation Training Centre was awarded to Western Australia. At the same time, the Research Hub for Offshore Foundation Systems was also awarded to UWA, and one on mine site remediation was awarded. But it was a significant event. It took about 12 months to get all the contracts done in place with all of the industrial partners in the ARC. And so we were able to launch in April 2016 at the end of the week in which the Global LNG 18 conference was held in Perth. Our objective, as it says, is to achieve cost-effective LNG production at all scales in remote or deep water locations. We were at that time looking at Prelude and also looking at the sort of growth of small-scale LNG, as well as helping the mega-scale plants that were already established on the northwest shelf of Western Australia and around the country. We had 10 industry partners. Logos are shown here, including a few from overseas, Samsung Heavy Industries and Daewoo Shipbuilding. From Korea in particular, China Guodian, whose name has changed a few times since then, but is effectively an energy company from China. And we had quite a good collaboration across many Australian and international universities, including with Professor Vishnu Parikh at Curtin University, Professor Paul Webley at the University of Melbourne, Professor Andre Luton at the University of Adelaide, and Dr. Tom Rufford at the University of Queensland, plus Professor Utek Seo in Seoul National University and Professor Young at the University of Auckland. A fundamental part of the mission of industrial transformation training centres is to produce industry-oriented PhD students, and the ARC includes funding for 10 12-week placements of PhD students with an industry partner each year. We decided to not just restrict it to the precise 10, but to actually expand it to a broader cohort of PhD students to maximize the industry training. And this has worked quite well, and we've shared this model with the ARC because often a particular student or a particular set of skills and the partner don't necessarily match at a given time. So having a broader pool is important. And already we've graduated many PhD students or those who have just finished or submitted, and a snapshot of some of them is shown here. We did these 12 projects, and they were grouped into sort of three themes. These were led by Professor Mike Johns and Professor Zach Amon at the University of Western Australia, and Dr. Kevin Lee, who's now at the University of Melbourne, led theme 3. The LNG industry is based on pretty well-established science and engineering, so making progress isn't simple, and you really have to go back and understand fundamentals better than has been done previously to make progress. And then the next important step is to demonstrate that new understanding translates to larger scales. And so the images showing here of our facilities that we've used try to reflect that process, as will the 2 examples I'll talk about this morning. You can see that there are a lot of projects, and they've all had very strong and specific outcomes that I think will make a material difference. Today I'm going to talk about just 2 of them, boil-off gas in LNG storage and transportation, and novel sensors, particularly for the detection of cryogenic solids in LNG production. So the LNG industry has been going for something like just over 5 decades now, and over that time it's grown exponentially with recent growth spurts, both initially at the beginning of the last decade in Australia, translating and continuing now in the United States of America. Global capacity for LNG is something like 400 million tons per annum. And you can see Karratha gas plant, which effectively started its first shipments back in 1989. It now has 5 LNG trains and was Australia's first mega-scale plant. And now we lead the world, just pipping Qatar in terms of about 80 million tons per annum of export. The growth in availability of cheap US gas has sort of driven that second growth spurt, with the United States likely to be challenging for world leadership in LNG by the middle of this decade. That cheap gas has had 2 big effects. First, the cost of gas, and particularly LNG, is now historically incredibly low, the sort of level that is 2 to 3 US dollars a gigajoule on the spot market, and sometimes there's even been examples this year of it going negative as people couldn't find places to put their LNG. But also it's helped the US in particular reach its emissions reduction target, as people have transferred to gas as a clean baseload fuel that has half the CO2 emissions. But we can't rest on our laurels, and there certainly is a big focus on continuing to improve efficiency, reduce fugitive emissions for the LNG industry. And central to that means we have to apply new technologies across the entire LNG supply chain, which is shown here, where we go from producing the gas in the wells to liquefying it at plants like the one shown below, then shipping, typically journeys across between continents that might take 7 to 14 days, where it is then offloaded, regasified, and connected to grids. And it's not just for electricity generation, it's also very important for heating and industrial powers, as well as transport fuels. Remember that electricity only is about 1/3 of all energy use. Fundamentally, though, the safe and efficient storage of the cryogenic liquid is a fundamental technology upon which the LNG business is built. And there are many different scales of storage. The ones I've just shown are the biggest, but if you're using this as a transport fuel, for example, or to power a remote mine site, you might be looking at this smaller scale, which might have LNG under quite a bit of pressure relatively. It's very important, the larger the scale, that you minimize what's called boil-off. And fundamentally, what a cryogenic liquid wants to do is to change its phase back into a gas. It heat will always come from the environment to try to warm it up, and then it will boil. So the challenge is what do you do with that? You might think, well, we understand boiling liquids pretty well, but it's particularly complex for LNG because it's a mixture, and the composition changes that occur as it boils off actually influence its properties very significantly. Another thing to keep in mind as you go to even smaller scales is that the costs of boil off and the costs of minimizing it vary greatly with scale. And so you need to have a general ability to describe what's likely to happen in various scenarios, not least of which to design the safety systems accordingly. The largest scale of LNG storage occurs in the megascale plants and then in the ships that transport them from the source to customer. And we're often talking about hundreds of thousands of cubic meters of LNG on these carriers. So this is a photograph shown here. And just to sort of give you an understanding of what we're talking about here, we have a tank on the left, cell A here. The liquid level is pretty high. You don't ship LNG unless the tanks are essentially full. The liquid, normally it should have sort of these convective cells where any heat is causing sort of the fluid to be well mixed. There's an inherent boil off of the gas, and this is producing a particular rate. But especially early on, what can happen is that the heat needed to boil off the LNG at the interface is drawn from the liquid closest to that interface faster than it's actually entering the tank from the environment. And this can lead to what's called stratification, where the top layer is actually warmer than the bulk. And what this does is it actually reduces the rate of boil-off gas production, which is good in some sense. It seems like we're not losing anything. But in the end, you can pay a price for this in many different ways. And one particular phenomena that's bad that people storing LNG need to pay attention to is known as LNG rollover. It also occurs in salt lakes and things like that. But in LNG, it's bad because it generates large amounts of gas that have to be handled by safety systems, which obviously don't like that, and it can have environmental consequences also. Typically, if everything's working well, the boil-off rate's about 0.1% per day, and that's quite a lot of energy, and you can't just vent it, or even there's much more than you need to drive the ship. So our industry partner Samsung wanted us to deal with a particular problem. So shown here, this is the LNG tank, say on a ship. The boil-off gas comes through, and here we have these BOG compressors, and they're part of the system for re-liquefying that gas and sending it back to the tank, with only a small amount being vented to the engines to drive the ship. And the key question that companies like Samsung want to know is how this critical piece of information called the boil-off gas rate, if you look at where it comes from in the design of these ships, it's entirely empirical. For different fill levels and different tank pressures, the vendor of those tanks provides charts which give you a boil-off rate. There's no computer model that people trust enough to be typing in and generating the numbers. And that's because it's a complex and scale-dependent process. It's hard to model, and it's also very hard to measure accurately, which is why, particularly at large scale, which is why perhaps no adequate tool is really available. So we set about designing and building a test facility at UWA for this. There have been many attempts at modeling, often involving CFD, but this doesn't properly handle the thermodynamics of that phase change, which is so important. And this facility was built by a PhD student, Fernando Perez, now working with Exxon in Victoria, and Dr. Saif Al-Jafri, still at UWA with us, to provide the high resolution data necessary to really understand all aspects of the phenomena. And we've also had several visitors from Samsung Heavy Industries visit us from Korea and spend a few months in the lab acquiring the data with us. For those of you that like detailed diagrams, this is one of the facility itself. That we can, the key point here is this boil-off gas cell, which is what we fill with the LNG. It can work at temperatures down to liquid nitrogen temperatures, minus 196 Celsius, and pressures as high as 10 atmospheres. We have a relief valve which allows us to control whatever pressure is building up here, and this allows us to do tests. The cell is about 6.7 litres in total volume. It can be filled directly, or we can actually liquefy gases inside if we need to. And it has something like 35 sensors that protrude in, temperature sensors, which protrude into the cell that allow us to measure not only the temperature profile in the gas and the liquid phase that's present, but also where that interface between the vapor and the liquid is. And we have a very good control of the temperature boundary, which through this copper can, which allows us to really define things very well and make sure our model of the system is working correctly. When you do experiments, you also really should compare them with models to test that what you're measuring is sensible, and then ultimately be able to scale the results to other scenarios. And so we've designed this software package called BoilFAST, which contains thermodynamic models as well as energy and material balances and heat transfer with only 3 parameters that describe how much heat flows in from the outside world, and then allows us to calculate as a function of time, either for the lab scale or for industrial scale tanks, what's going to happen in terms of the boil-off gas rate, the pressure build-up, and the composition of the remaining liquid, as well as its level. And you see this is part of our upscaling strategy. By doing well-controlled, well-characterized experiments, we can tune a very small number of parameters that have physical, well-defined physical meanings, and then we can validate them against predictions, validate the predictions of those models against data measured in the lab, and then ultimately provided by industry partners. The first step in this was making measurements of liquid nitrogen, and these are the results. Liquid nitrogen is simple because it's a pure substance. It's very well defined thermodynamically, and so it represents a very good way for us to tune the models and fix those 3 heat transfer coefficient parameters to force agreement between them. It turns out that our handbook estimates of those heat transfer coefficients were about right, but particularly the one between the gas and the liquid phase interface was very important. Now, our model doesn't yet account for stratification, and that's why in these early phases you see a difference between, for example, the boil-off rates, but certainly it can describe the pressure buildup and the steady state behavior of the fluid. And then the key point is to extend these model comparisons to tests of LNG mixtures with no further tuning allowed, no adjusting of those fudge factors, if you really want to convince yourself that you're measuring something that, and predicting something that is real. Our data clearly show 3 phases of the boil-off phenomena: the pressure buildup or the self-pressurization, a transient phase, and then that steady state condition. And it's during the first 2 that we can clearly see the liquid phase stratification take place, where basically the boiling at the interface is borrowing heat from the liquid locally and causing its temperature to be decreased relative to the bulk. This stratification occurs and reaches a maximum, and that's when you see the boil-off rate slow down. And then once we achieve full pressure in the tank, it catches up and the liquid becomes homogeneous. So the data showed us that the various stages are intimately linked to liquid stratification. Importantly, we also looked at the effect of nitrogen. Nitrogen is an impurity that is hard to remove from LNG, and some of it is like 1% typically dissolved in the liquid phase. But it's the most problematic component because although it's heavier than methane, it boils at lower temperatures. So being able to predict and measure what's occurring in the LNG was a key achievement of the boil-off model. And then finally, the acid test, if you like, was to compare the predictions of these models with a test done by our partner, and they used an 850 cubic meter C-type LNG tank that was on the ocean at 3 various fill levels. It wasn't an actual carrier, but a facility that our partner had that reflects what is likely to happen. And the model did, although it's a very simple model, the scale up was successful. The biggest error being for the lowest amount of liquid, where the change in pressure is smallest. So this was a very encouraging result, and we're conducting future research to capture that liquid stratification with the next generation model. In the meantime, we've taken BoilFAST and even applied it to see if it works to describe the boil-off of liquid hydrogen. And there is some open data in the literature, for example, from the US Department of Energy, Lawrence Livermore National Laboratory, where they had a test with a 12.5 cubic meter tank of liquid hydrogen. And with no fitting, the model was able to predict the volume decrease as a function of time very accurately. So this is encouraging, and it shows the versatility of the model to go beyond the original application towards the description of other cryogenic liquids of industrial importance. I'm now going to turn to the second research outcome from the AARC Training Centre, and it's motivated sort of by the opposite problem to the boil-off case, and that's the formation in the liquid not of a gas phase but of a solid phase. And people are all familiar with and there is an analogy here with heart attacks, where the flow of the blood is blocked by solids, heavy compounds depositing and ultimately occluding arteries. And that analogy helps me to explain one of the major problems that can occur and does occur in large-scale LNG plants, more frequently than anyone would desire. Cryogenic heat exchanger is really just a bunch of tubes that are quite small, so that heat can be transferred from the refrigerant that's outside into the gas, and then ultimately the LNG that's passing through these small bundles of tubes. And any heavy impurities, and typically this can be water, carbon dioxide, or heavy hydrocarbons like benzene, if they're present in too high a concentration, they will actually deposit, build up, and block the cryogenic heat exchanger. And this chart, and the key diagram here is the yellow curve, which is the pressure drop across this cryogenic heat exchanger, is in some senses the signature of a heart attack in an LNG plant. It's very slow. The plant was operating normally. This is from RasGas Train 4 in Qatar, and it was presented in Perth in 2016 at the LNG 18 conference. But they had a problem in August, and by December, the pressure drop was so big because of the solids depositing that they had to shut down. And shutting down LNG plants is a significant economic penalty. You're going to miss contracted shipments, so the order of expense is at least on the order of $10 million at that mega scale. So our first strategy was to work with Chevron and the GPA to update the tools available to industry to predict the risk, in particular, of these solids freezing out. And this led to our free software package called ThermoFAST, which the video is showing you how to use it. We're posting in there the composition of the RasGas LNG. We're generating a phase envelope, which many bits of software can do, but the key feature of the ThermoFAST tool is the ability, it's been optimized to predict when, what temperatures solid will form from the LNG. Every LNG is different. The more LPGs or propane, for example, that it has in it, the freeze-out temperature for a particular impurity will also vary. There were data in the literature from the 70s, but the tools available were not particularly modern. And with ThermoFAST, we were able to tune to that data, get a much better representation in a more general context, and even be able to generate very efficiently so-called solubility charts for particular LNGs. So this has just been calculated by the ThermoFAST program there, and you can see if you're at these temperatures with this concentration of benzene in this particular LNG, the solid is going to come out of solution. So you want to make sure your operations stay down in this region. But having a model is fine. You also need new data. So we set about experimentally designing systems that would allow us to visualize the freeze out of these solid impurities. And our first version of this has done a significant amount of work in generating new data that really have helped improve the models in ThermoFAST for industry's use, looking at methane benzene, p-xylene, neopentane, basically systems for which the data were either inconsistent or didn't exist at all. The basic idea is we have a high pressure sapphire cell which we fill with the LNG, and a copper tip protrudes into the fluid, which is being stirred by this stirrer. The copper tip is cooled relative to the bulk fluid, and this causes solid to come out of the solution when you reach the solubility limit. We can then reverse the temperature of the fluid of the copper tip and measure when that fluid melts. And what you're seeing here is actually there is a difference between the freezing temperature and the melting temperature of a solid, which is important. The melting temperature is what models like ThermoFAST predict. So this allowed us to tune or validate ThermoFAST predictions. One of the most surprising results that was predicted by ThermoFAST, and we first saw this coming out of the model, we were wondering if there'd been an error in the coding or something, is this phenomenon of retrograde freezing. And that means that you've got a fluid mixture and you've got a solid present, which is bad. And normally people would heat things up to get rid of that solid. But actually, in certain LNG mixtures, you can cool it down and the solid will redissolve. So what this video is going to show is that that phenomena that was predicted is real. Here we have the copper tip. It's a little bit difficult to see, but you can see that the temperature of the copper tip is cooling, it's dropping. And if you watch the surface carefully, what you'll start to see is particles and the film of solid on that tip disappear once the temperature stabilizes. There's specks on the window that are in front of it, but you can clearly see the before and after picture of cooling validated that prediction from ThermoFAST of retrograde freezing. And so potentially, and this is a bit speculative, this offers another operational strategy in some cases to consider when trying to fix blockages. But we also realized that to look at very low concentration systems like those found in industrial plants and to examine the kinetics, we needed better resolution. So we've since built a CryoScope facility, and Aman Siavashi, who built the primary cell, also helped a new PhD student, Catherine Sampson, and research fellow Dr. Peter Metaxas design this this CryoScope facility here. And so essentially you have a high pressure cell that's got a sapphire window. It's inside a vacuum can, so we can get it to very low temperatures. And we're looking at it through a microscope. And we have, again, a copper tip, which allows us to cool that liquid relative. It's being stirred. You can't see the stirrer. It's off camera. But as that copper tip is cool, you can see the benzene here coming out of solution. So we're tracing this pathway into the phase diagram, and the solids are coming out at these temperatures. And this really gives us a sense of the morphology, the kinetics of the growth, and then allows us to really derive a deeper understanding of what's likely to happen if this problem occurs. And so recently we've been looking at experiments with 100 ppm benzene and methane. We're getting, what we really want to get down to is about 10 ppm benzene, and that is possible. So these are still images now before and after at 500 microns in the scale bar. You can see these small specks of benzene coming out of solution. And if we repeat this experiment often, we see that the formation occurs at a particular subcooling compared to the predicted equilibrium boundary. And that allows us to actually build up probability distributions relating to sort of the nucleation sites and the subcooling required to cause the solids to form. And so we can actually generate probabilistic models to predict the risk, with an actual probability as a function of how low below this melting temperature that the cryogenic heat exchanger might have been and how long the fluid has been within that phase boundary region. So finally, I'd like to talk about our third step, which is to develop an automated sensor for better LNG plant operation. While the tools I've just shown you are good for the lab, they're not particularly applicable for use in a plant. Windows in particular get fouled and you'd need to have someone interpreting the data. Currently, what plant operators do is they use just a composition analysis, which is a relatively low resolution measurement, so it doesn't really even distinguish benzene from something that's got a similar molecular weight like hexane, to calculate whether or not there's going to be a problem. And here's the cryogenic heat exchanger in the LNG plant, and the RAS gas problem occurred in this cold bundle up here. So these heuristics really are quite limited. And our concept was, well, why don't we actually develop a sensor that is non-visual, that is robust, and it can be put upstream of the scrub column where the last separation of heavy hydrocarbons occurs, and it'll actually measure the freeze-out temperature of the current feed gas in real time. And you won't have to use a model with some poor compositional information to try to predict if and when there's going to be a problem. And in addition to this real-time monitoring, from the freezing temperature that you detect, you will be able to know what the highest concentration or problematic impurity is, and you'd be able to use that sensor to test remediation strategies like dosing in a little bit of LPG to help redissolve the fluid. And it's not just about protecting against a negative. You can actually increase the throughput of the plant. In other words, you can process more gas if you can show that actually there is no risk of freezing out using a sensor, because the processing is adequate. Or you can reduce the amount of energy being spent removing particular impurities, either in this unit operation or earlier ones. So we need it to be sensitive to all of and any solid that can freeze out, including the most problematic ones, which are benzene, CO2, and water in LNG plants. And so we've developed a cryogenic solid sensor, which is based on microwave technology. It's pretty simple in design, and it's been led by PhD student Matthew Hopkins and my colleague Dr. Paul Stanwix here at UWA. It's just a pressure vessel. It's got a copper cold spot, and then this sort of reentrant cone that when you assemble the lid produces a gap. And that gap is where the solids are going to form. Now, most of this, the space in the sensor is not doing very much, but what we can do, a bit like your microwave oven at home, is we can actually excite the microwave fields, and this geometry makes the fields very sensitive to the refractive index, really, of the whatever is in this gap here. And so if this cold spot forces a solid to form, the refractive index changes in this region, and unlike in your microwave oven, we're not heating the fluid, we're just sort of measuring a frequency that allows us to know what the refractive index really is. We can see when that solid forms, and different solids have different refractive indexes. So this is particularly a useful design because it's compact and robust. There are no windows. We can match that material to be the same substrate as the material used in the heat exchanger. So it could be aluminium, for example. And because of the ability to measure refractive index, we can actually calculate the amount of solid that is being deposited as a function of temperature for a given fluid of concentration. So the sensor, we've built it, it's operating in our lab, and we can use it to do tests of industry fluids. The mode of operation in terms of its byline sampling. Here's the sensor itself. Much of this equipment is to help cool and control the temperature, as shown in this diagram here. The fluid comes in, it flushes out that spot and can either be operating in a batch mode, or we can continuously flow the fluid through the sensor, purging continuously that region, although any solid that deposits sticks there and allows us to get even better signals over time. And this particular version uses liquid nitrogen, but we've also developed a cryogen-free thermostat based on a pulse tube apparatus, so you don't need liquid nitrogen even to run this sensor. And to just demonstrate some performance, here's CO2. We have 53 parts per million of CO2 and methane. ThermoFAST predicts the melting temperature to be around 99 Kelvin. It's a high pressure liquid. The yellow data is coming from our sensor, and this is sort of like a baseline. It's a bit like tearing your kitchen scales. You can choose the 0, but there's no question that when the solid forms, we start to see solid CO2 plating out in our sensor. We can also do it with benzene at 100 ppm currently, and now being pushed to lower concentrations. A very nice signal. Benzene doesn't have the same refractive index and tends to be a bit fluffier than CO2 solids, so it's sometimes a bit harder to see, but also we're getting quite large amounts of solid being detected. With water, and this is very recent results, so we're still pushing sort of the envelope here. These data are literally about a month old, and this is with 200 ppm water and methane. So really, this is actually quite a high temperature in an LNG context, but you can see that it's a very sensitive measurement. And when we heat it back up, the hydrate melts at the same temperature as expected from the equilibrium prediction. So to conclude, after 4 years, the Australian Centre for LNG Futures has successfully trained many talented industry-ready PhD students, and we've delivered many important research outcomes. And I've talked about 2 of them today, one which was relating to LNG boil-off and our software tools for describing it, and another relating to LNG plant blockages caused by cryogenic solids formation, tools for industry to use today, and a patented sensor to come in the near future. Coming soon, as one of the things we're working towards is a web-based version of ThermoFAST, so engineers and companies don't have to install software locally. IT departments are very strict nowadays, so having access to ThermoFAST on the web will be, we think, particularly useful. And that work's been led by Dr. Peter Falloon. He'll be talking about it next week in our group seminar. So with that, let me say thank you. And if there are any questions, I'd be happy to take them. This was a photograph of our first Christmas party back in 2016, and one of my favorites for showing off how lucky we are in Perth. Thank you.
Thank you, Eric. If everybody would like to, if they have any questions and you would like to ask those of Eric, please raise your hand, and Eric will be able to identify you and and you can ask your question.
The raise hand button is on the participants pop-out tab for those. Michael Breer from the University of Melbourne. Thank you for asking a question. Oh, can we unmute Michael? Yep.
Good morning in Perth, and hello to everyone wherever you are.
You're a bit soft, Michael.
Oh, I'm sorry. Hang on. Can you hear me now?
Yes, that's great.
That's great. Okay, I'm sorry. Good morning in Perth, and hello to people wherever you happen to be. That was terrific. Thank you very much, Eric. I thought, I mean, as you know, I work in fluids and some cryogenic and flash boiling, but not as a chemical engineer, and more in looking at fuel injection and engines and other such things, where the thermodynamics of a lot of these problems are tightly coupled to the fluid dynamics of these problems. So I'm just asking a more general question. Is it, for example, looking at a large LNG tank, do you have some thoughts as to how you might couple, for example, the full fluid dynamic problem with this very sophisticated thermodynamic thinking?
Yeah,
my experience is that's computation extremely challenging.
Yeah, it is, and I don't have a clear answer on that, because the CFD is particularly important, but it definitely needs to be anchored to that thermodynamic modeling. And the thermodynamic modeling you can, and we do use for flows in pipeline, various tools such as those that are implemented in Olga to describe pressure drops and the various distribution of phases in a particular flow. But yeah, I think that's one of the outstanding problems in terms of really combining now this thermodynamic description with rigorous hydrodynamic models of what's happening as you take it from the tank and you use the LNG. And I think that's an area of research that we'd be happy to work on in the coming years.
I think it's a fascinating area, and the little I know about the bit I know about the interaction between the thermodynamics and the fluid dynamics is that the coupling is very strong, and therefore if you oversimplify your thermodynamics, you get the wrong answer, and if you oversimplify the fluid dynamics, you get the wrong answer as well. So it's a truly challenging problem. But thank you, Eric. It was a fascinating talk.
Thanks, Michael. Yeah, I agree with that statement about, even in the tanks, we have started to, it's a relatively static environment, but those convective flows are sort of important to understanding the evolution of the temperature profiles. So if we can do that in the first instance, maybe there's hope for more challenging applications. Okay. I think it looks, it's Mr. Sutherland, is it?
Yes. I don't know, can you hear me?
Yes, we can. Sorry, I haven't met you before, but please go ahead.
Coming out of the US, so my sound may be a little bit delayed, right? I was just curious, a little bit obscure, but you showed a slide where you applied your data to hydrogen. And I was wondering, and you did it without any adjustments, but I was just wondering, why did you expect that, given the orthopara hydrogen issue in liquid hydrogen and its effect on the thermodynamics of boiling?
Yes, so the way we did that, and it is, we haven't published it, literally it was done about a week ago. Temperatures, once it's a well equilibrated liquid, it's all parahydrogen essentially, and the thermodynamics of that effectively pure substance is well described. So I think the problem you're referring to, which is a very important one, effectively was mitigated by the fact that the fluid was being under storage for a while there, and so not that surprised perhaps by given the work we've done building up the rigorous model that it does work with liquid hydrogen. But what we'd like to do, of course, is expand it to deal with the mixed case, which will occur during the production stage in particular, and or if it's produced and then stored without fully accounting for that conversion, for which there are not really many good models. At least, I know my colleague Jacob Leachman might disagree with me there, but I think at least work needs to be done in that space. So anyway, yes, I hope that answers your question. I think it's an area we'd like to go in our future research with dealing with that orthopara thermodynamics description.
Yeah, I appreciate that. Yeah, we've had a couple of people asking if they could use our Raman instrumentation for that, and So that's something I'm kind of curious about myself. I know spectroscopically, yes, but we haven't actually done it. So.
Yeah, it can be done, and it's just a matter of doing it in a way that's useful. And with Raman, we played with it a little bit ourselves too. But I think that's going to be an important tool for sensing. There are others as well, like NMR, that can in principle be used to monitor it. And I think that monitoring of the conversion from ortho to para as you cool the liquid hydrogen is going to be one of the well, not enabling technologies, but a technology that really helps make hydrogen production, liquefaction, much more efficient.
I appreciate it. Thank you.
Li Guang, he's got a question.
Yeah, it's Liang Guang. I'm from the CSIO in Melbourne. Yeah, I have a question about the boiling off things. When you are doing the model, like when the LNG tank, they are with the when I deliver things, I think along the sea, then like a wave will cause the tank will be like vibrated. Do you model can consider like a this wave involved how it's affect on the boil off things? I think this is terminology called sloshing.
Yeah.
Sloshing, yeah.
Yeah, so our model is not considering the hydrodynamics of the tank. In a sense, that's why those tanks, when they are shipped, have to be effectively above 90% full because of sloshing issues. There has been some research into sloshing, and if you have it half full, you can get very high pressures that can damage the tank as a result of that sloshing phenomena. Actually, though, on ships and in big tanks, the model is likely to work better than in the small lab systems that we test, because the motion of the ocean causes the LNG to become well mixed, and it tends to be more homogeneous in the larger scale fluids. So, in a sense, the inherent assumptions in our simple model, remembering we haven't quite extended it to stratification yet, are improved or are more correctly realized in the ocean system than in our lab. So in a sense, that mixing helps. But yeah, sort of along the lines of Michael's earlier question, this combination of the hydrodynamics with the thermodynamics is going to be important, particularly if you want to ultimately design tanks that can be shipped that are not necessarily completely full.
Okay, thanks. Yeah.
Thank you.
Thank you.
I don't know if there are any further questions. If not, I think I'll let people get back to their busy days. Jill, do you want to say anything further?
Yes, thanks, Eric. I'd like, on behalf of everybody, I would like to thank you for this morning's public lecture. That was absolutely fantastic, easily for everybody to understand, even for people who are not directly involved in the types of research. So I'd like to thank you very much, and thank you everyone for attending from wherever you are. Much appreciated, and enjoy the rest of your day. Thanks.
Thank you all.